So now we see why random noise can become a realistic image. In the last video, we saw how AI turns noise to art, and we saw how an image is first noise is first added to an image, an image is blurred out, and then the noise is removed to retrieve the image. And we've seen this as a pattern for image generation in AI. So let's see. This is like an advancement of that same idea. So why random noise can become a realistic image, and we'll see the mathematics behind diffusion models, which talked about in the last video, talking about forward diffusion where you add noise, and reverse diffusion where you remove the noise to retrieve the image, under discussion. So the learning objective, for the learning objective, at the end of this lesson, we'll understand why random noise can become a realistic image, the mathematics behind the denoising process, the concept of probability flow, how diffusion models generate high quality images, and how to implement simple denoising algorithms in Python. So the big question is image switching on an old analog television. Okay, imagine switching on an old analog television. Instead of a picture, you see random static everywhere. So it looks something like what you have here. So you have all this blackness, you have all this gray and all these kind of signals. Now imagine someone tells you inside this random noise is a beautiful cat. Now, can you ever imagine that there's a cat somewhere in all of this noise you have here? So now imagine someone tells you inside this random noise is a beautiful cat. That sounds impossible for sure. Yeah, this is exactly what modern diffusion models do. They begin with pure random noise and gradually transform it into realistic faces, landscapes, paintings, scientific illustrations, photorealistic images. Now, the natural question is how can complete randomness become something meaningful? The answer lies in mathematics. So it's all about the maths, right? And that's why this playlist is the mathematics of artificial intelligence. Now, let's go and ask ourselves about the idea of randomness. What is random noise? Now, did a playlist on spectral analysis, and then we got to talk a lot about filtering. We got to talk a lot about frequencies and how to filter them and to remove noise and everything. An image is simply a collection of pixels. So each pixel stores a number. So for a grayscale image, for instance, 0 represents black. 255 represents white. So a random image assigns every pixel a random value. For example, if you have 1, 1, the value can be 201. 1, 2 pixel, you have the value can be 17. 1, 3 is 143. 1, 4 can be 81. In this way, there's no structure, no edges, no objects, no meaning in particular. But mathematically, diffusion models assume the random image is sampled from a Gaussian distribution, X, which is normally distributed with mean 0 and the standard deviation I. So where the mean is 0 and the covariance matrix which you have right here is the identity matrix. This is called the standard Gaussian noise. So mathematically diffusion models assume the random image is sampled from this distribution. So, and we have a good example of that here. You have a simple Python code generating noise. So generating the random Gaussian noise. So here we use just NumPy and matplotlib for visualization. So you just create the noise. So you just say you take the random function, then the number of the dimension of the randomness. That's what rand n is about. So that's you have 128 by 128, and then plot.im show the noise and make it gray. Of course, you can change the color map also from gray to whatever else. Then you have the random Gaussian noise. So no axis here because we just want to see the plain figure. So, and that's why you end up getting this random Gaussian noise. You can change the color map, like I said the other time. For instance, one other color map I like apart from gray is rainbow. Okay, this is great for now. So for the rainbow one, if you run it now, you see it's looking this way. So we can take it back to gray like that. All right. Now the question is, why do you start generating an image with noise? Why? Why exactly? Why can't you just generate the image? A natural question is, why not start from a blank image? The reason is that Gaussian noise has a simple mathematical distribution that is easy to sample from. During training, diffusion models learn how to transform this simple distribution into the complicated distribution of natural images. One useful analogy is sculpture. A sculptor begins with a solid block of marble. Inside that block lies every possible sculpture. Likewise, inside random Gaussian noise lies every possible image. And that is why when you try to generate an image using AI, it first starts with some things you can't really figure out until after some time you then find the picture. So the neural network simply learns how to reveal the image that is hidden in the Gaussian noise. So let's talk about forward diffusion, which we talked about in the last video already. During training, the model intentionally destroys images. That's during images, the model intentionally destroys images so that it can then reverse the process of destruction to reveal the image. Suppose we begin with a photograph of a cat. Say you have an original cat, and then you add a little noise. You have a slightly noisy cat. You add more noise. Then the picture becomes blurrier and blurrier. Then you now have a very noisy cat now to the point that you may not even be able to tell to figure out if there was a cat there if you didn't know how it all started. Eventually, you have pure Gaussian noise, and the cat is nowhere to be found technically. So this process is called the forward diffusion process, adding noise to a clear picture until the picture is unrecognizable. That's forward diffusion process. At every step, a small amount of Gaussian noise is added. Mathematically, you have x sub t equals square root of 1 minus beta sub t, x sub t minus 1 plus square root of beta sub t multiplied by epsilon, where x sub t minus 1, this here, is the previous image. This is the previous image. Beta sub t is the noise schedule. Of course, so the square root of the noise schedule multiplied by epsilon. Epsilon is the noise that is normally distributed now. So after many diffusion steps now, you now have x sub t to be approximately normally distributed with mean 0 and variance I, identity matrix. Eventually, every image becomes random noise as you keep adding noise like that. So it ends up becoming like the original noise as you keep adding more and more noise. So example, suppose the original pixel is 120 and the noise is 40. Beta is 0.25. So find the pixel value after one diffusion step. So the solution is simply this. You first compute square root of 1 minus beta. 1 minus 0.75, which beta is 0.75. Square root of 0.75 is square root of 3 over 4. That's like root 3 over 2, which is 0.866. Also, square root of beta, which is square root of 0.5, is simply 0.5. That's square root of 25 over 100, right? That's uh 25 over 100. That's 4 over 10. No, 5 over 10 actually. So therefore, X1 can then be 0.866 following the formula now, following this formula, 1 minus square root of 1 minus beta and all that. So you have 0.866 times 120 plus 0.5 times 40, which is 103.92 plus 20 equals 123.92. Imagine the original image was 120. Now it has become 123.92, so it has become noisier. So only a small amount of randomness has been added because it is just one step. So if you keep doing that, you're going to have a whole lot of noise at the end of the day. So you can write a simple Python code for that also. So you have the original image 120, the original pixel 120, the beta, that's we saw beta up there. That's the noise schedule. That's the noise schedule. So which is 0.25, and then you add noise 40 noise. So x1 then this is the formula now. Square root of 1 minus beta x plus square root of beta times noise. So then you can print the pixel after one diffusion step, which is x1 here. So pixel after one diffusion step is exactly what we got here, 123.92, just like what exactly this code is giving us. Now, that's forward diffusion process. Now, how about the reverse diffusion, which is the denoising process? That is the reversal of the noising process, so to speak. So the forward process destroys images, while the reverse process reconstructs them. So it removes the noise. It denoises the image. So instead of adding noise, the neural network learns to remove it. So you have an image that is noise, more or less noise, and then you have less noise. You keep removing the noise, then you have a clearer image, and at the end of the day, you have a realistic image. And that's basically the process. At every step, the model predicts the noise contained in the current image. It then subtracts this predicted noise. Repeating this process hundreds of thousands of times gradually reveals a realistic image. So this is what happens. That's why when you're generating an image, it is slower compared to when you're just generating normal text. So the denoising equation, the neural network, So now, in looking at the denoising equation, the neural network predicts epsilon sub theta of x sub t comma t, which estimate the noise inside the current image. So it estimates the noise inside the current image, and then the reverse diffusion equation is then x sub t minus 1. So you are retrieving x sub t minus 1 back, the original thing, from the one that has been noised up, so to speak. So x sub t minus 1 equals 1 over square root of 1 minus beta sub t into x sub t minus beta sub t all over square root of 1 minus alpha t uh, hat, or alpha t cap. What's this thing called? Alpha t bar, yeah. So epsilon theta rather, into x t comma t plus sigma sub t multiplied by z, where epsilon sub theta is the predicted noise, sigma sub t controls the variance, z is the Gaussian noise, then alpha sub t bar is the cumulative product of the noise schedule. This equation is repeated many times until the final image is obtained. So that's the denoising process. Imagine now you have a current pixel of 150 and the predicted noise is 20. So the denoised pixel becomes 150 minus 30. So the predicted noise is 30 rather. So the denoised pixel becomes 150 minus 30, which is then 120. Suppose the next predicted noise is now 10. You have the pixel becoming 120 minus 10, which is 110. So you have less pixel compared to when you have the noise stop image. Repeating this procedure gradually reconstruct the original image. So we have that simple thing here. Original pixel 150, predicted noise 30, remove that, you get 120. So keep removing until you get something, until you get a clear image. Now, question, what does the neural network learn? So, the whole AI thing is about learning, right? You start with something and then you keep iterating. That process of iteration is learning, reducing the loss function until you get a loss as close to zero as possible, such that you get maybe the image or whatever it is you're looking for, that is actually acceptable to you. So the neural network does not memorize images. Just like neural network, AI does not understand words. It does not also understand images. It only understands so in the case of images, it understands noise. So the neural network does not memorize images. Instead, it learns the noise that was added. So it sees everything from the angle of noise added, and then it tries to predict the amount of noise and keeps removing that noise until the clear image is obtained. So imagine you impute a noisy image and the output is predicted noise. So the learning objective is then to reduce the learning objective is L equals the norm of epsilon minus epsilon sub theta raised power 2, which is simply the mean squared error between the true noise and the predicted noise. So you want to see how well you're predicting the noise in the image. And then you want to make sure that your prediction is as good as possible. So let's say true noise is 20 and the predicted noise is 18. The loss becomes 20 minus 18 all squared. That is 2 minus 2. That's 2 squared, which is 4. So a smaller loss means the model predict the noise more accurately. So the more accurately the noise is predicted, the better it is to remove that noise and then predict the next one until a clear image is obtained. So just like what we have here now. So true noise is 20, predicted noise is 18 pixels. Then the loss is true minus predicted noise raised power 2. So, and that the loss becomes 4, like we have here. So it's simple math, so we can easily compute that manually. So probability flow. The denoising process can also be viewed from the perspective of probability. Initially, the image is sampled from a Gaussian distribution. As denoising progresses, the probability distribution gradually changes until it matches the distribution of real images. So instead of suddenly jumping from noise to an image, the samples continuously flow through probability space. The probability flow equation then is dx dt equals f of x sub t minus 1 over 2 g of t squared, then grad x log p sub t of x, where p sub t of x is the probability density, and grad sub x log pt of x is called the score function. So this is the score function right here. So f of x comma t is then the drift. So this is the drift right here, and then g of t controls the diffusion strength. So the score function always points towards regions of higher probability. So the score function, this whole thing, always points towards regions of higher probability, guiding random noise toward realistic images. So in this case now, imagine this simple code here. Import number as NP, import matplotlib. Of course, number is for numerical computations, and matplotlib is for visualization, for seeing, for visualizing whatever you're doing. So we have random seed. Now random seed is actually there for to make sure we always get the same result, because we are using the random function in line 6 here. So if you don't have this seeding, each time you run it, you're going to get a different result. Basically, that's why we have that. Then you initialize here, we have the history. So for everything in the range 20, you then have this x, which is x minus 0.1x. So then you append whatever you get now. You copy this x now. You append it to history. So this history, keeps going until you get to from 0 to, I think, from 0 to 20 or 1 to 20 here. Then this helps to visualize it. So you have a figure size that is 7 by 4, and then you have the history at the initial stage. You have the bins. Then you have history at -1. That's history at the final stage, more or less. So initial is 0, final is -1. That's from the back now. So then you plot the legend. So, and you have the plot title. So you have a simple probability flow shown right here. So you can see the initial, the initial, uh, the initial distribution you have is all this blue thing here. So which is such a wide range, but the final one is narrower. So you have, so this is a simple probability flow at the end of the day. So you can see that the final one is more direct, uh is narrower compared to the initial stage, which is all over the place. So now why does this actually work? The diffusion model solve an easier learning problem. Instead of generate an entire image from nothing, they ask, can you remove a tiny amount of noise? So removing a small amount of noise is much easier than creating the entire image. So by repeating this simple operation many times, a realistic image gradually emerges from Gaussian noise. So in summary, we are saying that in this lesson, we learned that images are gradually destroyed by forward diffusion. So noise is added gradually until it becomes totally unrecognizable. And then Gaussian noise is added at every step. That's what happens. Then the neural network learns to predict the added noise, and then reverse diffusion removes the predicted noise. Probability flow describes this process continuously. So modern AI image generators use this mathematical framework to create realistic images from pure random noise. So when you prompt ChatGPT or whatever to generate pictures for you, so it doesn't start by just generating the picture. It starts with a noisy image and then removes noise until the image you're looking for actually does emerge. So we have some practice problems, and of course I get to solve two of them. So here you can see questions 1 to 10 of the so there are 20 questions in all. So I'll be solving 11 and 15 here. So here you have questions 1 to 10. Try your hands on them. Then, so question 11, I'll be solving 11, which is the kind of thing we did already before. So a grayscale pixel has value x equals 100. Suppose beta, that's the noise schedule, beta is 0.16, and the sampled Gaussian noise is 20. Use x1 equals square root of 1 minus beta x plus square root of beta epsilon to compute the noisy pixel value. So you see that 11 clearly. And then the other problem I'll be solving is 15. So you can see 12 and 13 right here. See 12 and 13. Then 14, you can see 14 and 15 here. So for 15, suppose the true noise values are 12, 18, and 25, and the predicted noise values are 10, 20, 22. Compute the mean squared error. That's pretty easy to compute. So I'll be doing that too. Then, of course, you can, okay, I don't know, I don't think you can see the rest here. So that's 15 right there. Okay, yeah, we can see the rest. So this is now 16 to 20. You can see all of 16 to 20 here now. So let's go ahead and solve 11 and 15 as to bring this whole idea home. Why random noise can be, um, why random noise can become a beautiful image, can become a realistic image, yeah? So it starts with noise, and then we get a beautiful image at the end of the day. Imagine. So let's go ahead and do 11 and 15. So problem 11, a grayscale, a grayscale pixel has value. X equals 100. Suppose beta, that's the noise schedule, is 0.16, is 0.16, and the sampled Gaussian noise is epsilon, which is equal to 20. Then use x1 equals square root of 1 minus beta x plus square root of beta epsilon to compute the noisy pixel value, the noisy pixel value. Okay, so let's do that. Solution. So we know X is 100, that's the pixel value. The noise schedule, beta is 0.16, and the Gaussian noise is 20. We have all of that. So using the forward diffusion equation, x1 is equal to square root of 1 minus beta x plus square root of beta epsilon. So we first compute. Okay, well, let me not just go that slow way. I'll just do everything at once. Okay, using forward diffusion equation, right? That we can have now x1 equals square root of beta is 0.16. That's 1 minus 0.16 multiplied by x. X is 100 plus square root of beta, that's 0.16 multiplied by the Gaussian noise, which is 20. So this is what we have. So x1 now, mind you, we started with 100. So this is forward diffusion and when we are adding noise. So we started with 100. Okay, so this is square root of 1 minus 0.16 is 0.84 multiplied by 100 here plus square root of 0.16 multiplied by 20. So that is x1 equals square root of 0.84 is approximately 0.9165 multiplied by that by 100 plus square root of 0.14. So that's 0.4 multiplied by 20. So now x1 is 91.65 plus 0.4 times that is simply 8. So that's 8. So we then have x1 to be 9.65. I mean 91, that's 99.65. Okay, I don't have to do that. Okay. 99.65. Interestingly, this is supposed to be forward diffusion. So, and it's already removing the noise. So the image is getting less noisy. So based on this particular result. So it's all about the parameters we are working with. So that's about question 11, problem 11. Now let's go for problem 15. Problem 15. So for problem 15, it says the true noise, the true noise values are 12, 18, 25, and predicted the predicted noise values are 10, 20, 22. find the mean squared error. That's what we are looking for. I guess I want to go green. Okay, this is green already, I think. So let's go green for the first time. So I mean in a long time that is. So solution. So the mean squared error, the mean squared error, MSE, is given as MSE equals 1 over n, summation from I equals 1 to n of all the epsilon i's minus of all the epsilon i's. Oh, did I change that? All the epsilon i's minus epsilon I cap, all squared. So what we mean by epsilon I is that the original values. Then epsilon I caps as the predicted values. So in essence, we are saying that the epsilon i's are all these 12, 18, and 25. And the epsilon I cap are 10, 20, and 22. So then we can have MSE. MSE is now, we have 3 data points, right? We have 3 data points. That's 1 over 3. Oh, okay. That took a bit of time to change. Okay. So MSE is equal to 1 over n, right? So 1 over n. So we have 3 data points. That's 1, 2, 3, 1, 2, 3. So normal 3. So n is equal to 3 that way. So we have 1 over 3 into, then we talk about summation, right? Summation of the difference, each of them squared. So we have, that means we have 12 minus 10 all squared plus, so this is this 12 minus 10 plus 18 minus 20, that's 18 minus 20 all squared plus 25 minus 22 all squared. This is the summation now. This is what the 1 over 3 and the square of each one like that. So that's what we have. So we then say MSE is equal to 1 over 3 into 12 minus 10, that's 2 all squared. 18 minus 20, that's minus 2 all squared. 25 minus 22, that's 3 all squared. 3 squared. So that MSE now is equal to 1 over 3 into 2 squared is 4. 2 minus 2 squared is 4. 3 squared is 9. So that MSE is equal to 1 over 3 into 8 plus 9, that's 17. So 17. So that MSE now is approximately 5.67, like that. So, and that's how that goes. So that's the mean squared error in that case. So with this, we come to the end of this interesting video. We come to the end of that, talking about how we end up getting realistic images from noise, from random noise. So let's go back. I'll just show the questions and then end the video. All right, so let's see the questions again. You have conceptual questions basically. What happens if the values of beta t are chosen to be too large? You know, uh, so it's more like technically some kind of learning rate here, so it can start jumping all over the place, I suspect. Then of course we did 11. We did 11. Then you can see 12 here. So you see 13 and 14. Then I did 15, or you can see 16, 17 also, and then the rest. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If there is so if you have subscribed to this channel already, I thank you very much for doing that. If you have not subscribed, you want to do that right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join, which gives you some special privileges. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.